All right, so this will be the last part of the lecture on Chapter 4. Just a little bit left here to go over on titration. Should be 15, 20 minutes at the most. Titration, like it says, is an analytical technique which you use to calculate the concentration of an unknown solution by reacting it or titrating it with a known solution. Most titrations, or the most common ones, are acid-base reactions, neutralization reactions. In this case, we're doing, an acid-base neutralization. So I have this flask here of an unknown acid solution, meaning I don't know the concentration of the acid in it. So it's some pH below 7. You're going to add some type of indicator. In the case of an acid-base indicator, it's going to denote the pH change when we hit the equivalence point, and it's going to show us a color change. Almost any indicators are going to denote some kind of color change. With this acid-base indicator, we're going to go from a clear solution to a dark pink solution. And then we have our burette here. This is an analytical tool used to dispense an exact quantity of liquid. So we have very fine gradations here along the burette to denote that specific volume. It's going to be filled with a base, in this case sodium hydroxide, and the base that it's filled with we know the exact concentration of. So we're using this exact base against an unknown acid. We're going to slowly add that base until we reach the equivalence point, or the point where the moles of the base are equal to the moles of the acid within the reaction. And at this point we're going to see that color change occur, so we know that our pH has gone up from an acidic pH to a neutral pH, or where that equivalence point occurs. And now by calculating how many moles of base we added to this flask, we can determine how many moles of acid are in there. So again, volume standard solution needed, moles of equal to the moles of solute in the standard solution, and then we're going to use our balanced equation. So if I have a mole of sodium hydroxide, I use the relationship between sodium hydroxide and hydrochloric acid. In this case, it would be a 1-to-1 reaction. So I know if I have a mole of sodium hydroxide, I have a mole of HCl, and then I look at the volume that I started with, that 20 milliliters, and I can find out the molarity by taking the number of moles and putting it over the liters. This just kind of reiterates again what we saw. So where titration is using a solution's concentration or determining a solution's concentration by reacting it with a known solution, and then again using that stoichiometry. Whenever we do titrations, we have to know the actual reaction that it's occurring and the stoichiometry, or the relationship or ratios between those reactants. So the acid-base titration we saw before, I have to know what the acid is, what the base is, the reaction, and the ratio. Is it a 1-to-1 ratio, 2-to-1, 1-to-2, whatever. And then we're going to add the known amount of solution to the unknown solution until the reaction's just completed. So we try to stop the second that the moles of our known solution are equal to the moles of the unknown solution. And this point, again, is called the end point. The reactants are in their stoichiometric ratio. So 1-to-1 or 2-to-1, whatever it is, we have that perfect mole ratio right there. This is sort of a close-up, cartoonic view of a burette. You've got your little stopper here for dispensing, and like I said, you have these very fine gradations, breaking it down into a tenth or a hundredth of a milliliter, so you can very accurately determine how much of that known solution you've dispensed into the unknown solution. Like it says here, the difficulty or the hardest part is hitting that endpoint and stopping. At first, you're going to see a very faint color change. You're going to go from that clear solution to just the lightest pink. If you over-titrate, if you go over by a single drop, you're going to right away go to that dark pink solution. Because pH is logarithmic, it's a base 10 scale, meaning that a pH of 1 is 10 times stronger than a pH of 2. This color change is going to occur, like I said, very rapidly. It's really just the difference between 1 drop or 2 drops. So the hardest part in the titration is making sure you're adding this drop by drop, watching very carefully for that color change. And as soon as you see the faintest amount of pink or whatever your color change by the indicator is going to be, as soon as you see that faint amount of color change, you have to stop. And if you do stop right at the endpoint or very close to the endpoint, you're going to have the moles of the acid being equal to the moles of the base. And this is going to give you the most accurate calculation for determining the concentration of your unknown solution. A little close-up view here. So I've got, in this case, the acid with the color indicator. I'm dispensing my base. You're going to see as soon as that base hits, the one point where the drop hits, until it mixes throughout the solution, it's actually going to be very concentrated base right there. So you might see in that small portion where the drop hits, the acid-base neutralization reaction actually carried out to completion. But once you mix it throughout the entire solution, a lot of times that color change will disappear. So you want to make sure your solution's always completely mixed. And once you do get it completely mixed, where the base is mixed all the way throughout the acid and that reaction is allowed to occur in the entire solution, we're going to hit that equivalence point now when the stoichiometric ratio is reached, and we see that color change indicated right there. So we know we've hit the endpoint in that solution. We can stop the titration. Example here on a molecular level, again, kind of a cartoonic view of what's occurring. I've got my base, or my oxygen, my hydrogen, my OH here in the burette. And my acids here, the protons, the H pluses floating around. And as they come into contact, the OH and the H form water. In this case, we still haven't reached that stoichiometric ratio. I've only got the two waters here. I still have 3 acids left, so I'm still going to need additional base to reach that endpoint. But once I do, once all the OH has reacted with all the H, we're going to see this pink solution. Now you'll also notice that this pink solution occurs at the endpoint, once we essentially reach a pH of 7. I can keep adding base to this. My pH is actually going to go above 7 to a basic pH, but I'm not going to see any noticeable color change anymore. So that's why you want to stop as soon as you see that pink color, because if you continue to go past that, you're going to miss the equivalence point, and you're actually going to be calculating the incorrect concentration of the unknown solution. And these are all, like I said, hopefully the visuals help. This is something that if you're continuing on, if you're going to take the 2046 lab or go beyond that into the analytical chemistry labs or anything like that, you'll actually be able to perform these titrations yourself. Hopefully, a lot of you maybe haven't done these. Hopefully the pictures help give you some idea of what it's actually like without having actually done the titrations themselves. So we'll go through, I think, a couple sample problems here. And that'll be the end of this chapter. So here we're told we're going to titrate 10 milliliters of a hydrochloric acid solution of unknown concentration. So we don't know the molarity. We don't know how many moles of HCl we have in that 10 milliliters. We do, however, know that we titrated it with 12.54 milliliters of a sodium hydroxide solution, and that sodium hydroxide solution was exactly 0.1 molar, or 0.1 moles per liter of sodium hydroxide. So what's the concentration of the unknown solution? So we're going to start with what we're given. We know the volume of the hydrochloric acid solution, although we don't know the concentration, and we know both the concentration and the volume of the sodium hydroxide solution. So we need to find the concentration of the HCl, find out how many moles of that hydrochloric acid we have, and then divide that by the volume, and that will give us our molarity, or concentration in moles per liter. Now again, we talked about that stoichiometric ratio, so we know the acid we're working with, and we know what base we're working with. So we need to make sure we have the correct reaction equation, and that it's balanced, so I know the ratio of the acid to the base, or how many moles of base is it going to take to reach an equivalence with how many moles of acid. So here we've got the HCl, the sodium hydroxide, the acid part, the H+, the base part, the OH-. They react to give us water and some salt. And if we look at the equation, we can see it's completely balanced, so I know that my stoichiometry is 1 to 1. 1 mole of HCl to neutralize 1 mole of sodium hydroxide. Or if we're looking at it in terms of the concentration, we have a 0.1 molar sodium hydroxide solution, so it's 0.1 moles per liter. So I know if I have the same volume or this molarity of sodium hydroxide and I have 1 liter volume, I should have 0.1 moles of sodium hydroxide. And then I would need 0.1 moles of HCl to neutralize or balance out that equation.